Okay, it's 8:30, so let's go ahead and get started today. All right, good morning, everybody. How's everybody doing today? Doing good, hopefully. End of week 9, so yeah, we're really getting there. So we're creeping up a little bit on our second midterm. So I think our second midterm is planned for week 11. Let me check again. Yes, week 11. So basically, our second midterm here it's half of it's going to be on our control volume stuff that we've been covering, and the other half is going to be on our differential flow analysis. So that includes potential flow and Navier-Stokes. And so, what we're gonna be doing, what we did yesterday or Monday, today, and all of next week will be on the next midterm. Okay. I'm hoping that we can have enough time for an in-class review session, but we are kind of naturally falling a little bit behind. So I might take up that class session before the midterm to kind of catch us up a little bit. But then, if I do have to do that, I'll do a pre-recorded review session just like I did last time. Okay. So there's also a new homework that's posted. So I think I posted that on Monday afternoon. And so it's a big homework assignment. So, I'm giving you guys a long time to work on it because there's a lot of stuff that's going to be covered in that homework. So make sure you get started on that, sooner rather than later. So the first half of it, you should be able to do already, which is just, more control volume stuff, but with energy and angular momentum. And then the second half of the homework, we'll be covering the stuff that we need for today and next week once we get into Navier-Stokes. Okay. Are there any questions on any of that stuff or anything we covered last time that I can answer before we get started? Okay. So let's go ahead and pick up where we left off because we have a lot to go today. Okay. All right. So where we left off last week was this idea of potential flow. Okay. All right. So the idea with potential flow is that it gives us a way to solve for basically the velocity field and the pressure field, okay? Or at least that's the goal, okay? Right. And remember, this is kind of a stark contrast to what we've been covering with control volume analysis, where control volumes we're interested in kind of the velocities and the pressures and certain quantities at certain locations within a control volume. But with differential flow analysis, what this allows us to do is to get a detailed picture of what the velocity and pressure look like everywhere in a domain. Okay, and so to do this, we introduced this idea of the stream function last time. And so the idea with the stream function was that it was a scalar function that can basically be differentiated to get the velocity components. Okay? Okay. And so we have both cylindrical coordinates and Cartesian coordinate versions of the stream functions. But just to kind of remind you, so in Cartesian, say we wanted to get the x velocity component u, we would just take the partial derivative of psi, where psi is our stream function. We take the partial derivative of psi with respect to y. And if we want to get v, we take the minus partial derivative of psi with respect to x. Okay. And so this is nice because with this stream function, we just have to kind of solve for just one thing instead of separate velocity components. So once we have the stream function, we can just take these derivatives, which are usually mathematically pretty simple to do, and we get our velocities. Okay. All right. And so where we left off was, actually solving for these stream functions. So what we said was if we require, well, automatically stream functions already satisfy conservation of mass, and so they're incompressible. Okay. Okay. And so if we also require that stream functions describe an irrotational flow, right? If we do that, then we found that our stream function satisfied the following equation, okay? Okay. And so this obviously, is a partial differential equation because we have derivatives in both x and y. And in fact, this is a very special partial differential equation called Laplace's equation. Right? We're not going to get into solving this because that's a whole class on by itself. I think Dr. Weiss teaches it. But we are going to leverage some of its very nice properties. If you remember from math, it's a lot of math things are not just solving the equations, but a lot of it is also what are some of the properties that these equations have. And there's one property that's going to be really useful for us as we solve these potential flow problems. Okay. Okay, so that was just a recap of last time. So are there any questions on this? Okay. Okay. And so, Laplace's equation, it's a very famous equation, but we're only really just going to make use of one property. And that one property is the fact that it's a linear equation. Okay. And so hopefully that term is ringing some bells. So maybe you took 308 before, or maybe from your math classes. Okay. And what we know for an equation that's linear is that we can take linear combinations of various stream functions, and the result will still be a stream function. Okay. Okay. And so mathematically, what does this look like? So let's say that we have our Laplace's equation here, okay? And this is the equation that our stream function should satisfy. And let's say that we have one stream function, we'll call it psi1, and this guy satisfies the equation. Okay? We also have another stream function psi2, and this one also satisfies the equation. Okay? And then we also have another stream function psi3. So all of these guys can satisfy this equation individually. And so if you have stream functions that can satisfy it individually, what you can do is you can just simply add them up and get a new stream function. Okay. And so this new stream function psi4, which is simply just the sum of psi1, psi2, psi3, this one is also a valid stream function. And so this is really nice because the way that we're going to proceed from this point is that we're going to look at certain kinds of flows. We're going to define their stream functions. So we'll call these basically the basic building blocks of potential flow. And then what we can do is we can then combine these different building blocks to get some really interesting and complex flows. And the way that we can combine them is we can just simply add them together, which is nice because that's usually pretty simple to do. Okay. Okay. Any questions on this before we start jumping into the building blocks? Okay. Okay. And so what I'm going to do now is I'm going to go over basically the four basic flows that you can define with stream functions. Okay. And so, the way I'm going to do this is I'm going to give you the name of the flow. I'm going to draw a picture so that you can kind of see how it is. And then I'm going to give you the stream function for it. Okay. Okay. All right. So the first one is just simply uniform flow. Okay. And so what I mean by uniform flow is that all the streamlines are kind of straight and parallel. So we have just flow going in one direction. Okay. And so let's say that we have flow going from left to right here, and it's going with the velocity of u. Okay. And so this u, even though it's kind of clear from this picture, this is just simply the speed of the flow. Okay. All right. And so at first, we're just going to define our uniform flow to be in the x direction, but I'll show you that we can actually angle this at any direction that we want. Okay? And so the velocity components in this case are just going to be simply v. U is just going to be big U, and v is going to be 0 because we don't have any flow in the y direction. And then connecting this to our stream function, we know that this is going to be d psi dy, and this is going to be negative d psi dx. Okay. And so we combine these together and we integrate, and we get the stream function for uniform flow, which is simply u times y. Okay. And so to get uniform flow in the x direction, we define the stream function to be big U times y. Okay. And so uniform flow can be used to model things like probably as everyone imagines how wind is, right? And so wind is usually going in one direction. And so we can define a stream function for wind to be just u times y, okay? And so if you notice, we pick y here because of the fact that the x velocity is given by d psi dy. And so it's the opposite because our derivatives are mixed here. Okay? All right. And so that's uniform flow in the x direction, but then what if you want uniform flow at an angle? Okay, so let's say that we want uniform flow at an angle like this. Okay? And so let's say here, we have an angle, we'll call it alpha. Okay? And so in this case, the velocity components are given by this. Okay? And so we have little u is equal to big U cosine alpha, and v is equal to u sine alpha. Okay. In this case, we have to modify our stream function a little bit. Okay. And so our stream function is going to be u y cosine alpha, okay, minus u x sine alpha. And so that formula that I have at the bottom there is another form for uniform flow when your flow is pointed at an arbitrary angle. Okay? And so most of the times, at least for the examples we'll see today, we're going to use the stream function that's in black right there, which is just u times y. But for situations where you want your uniform flow to be angled, we can use kind of the more general form in the bottom right there. Okay. And so remember, the way that we use these is that we're basically just going to stick this stream function in here. And then once we have a stream function, we can take the derivatives in order to get the velocity. So right now it seems kind of, a little bit inconvenient because since we know exactly what the velocities look like, going through this trouble of defining a stream function seems a little bit, weird and kind of inconvenient. But what you'll see is that, once we start combining these stream functions with other stream functions, it gets to be, a really convenient thing. Okay, any questions on this? Okay. All right, so that's uniform flow. So uniform flow is kind of our first potential flow building block. And so now let's go over source and sink. So, these are actually, two different potential flows, but I combine them together because they kind of flow the same thing. Okay? Right, so there's a question in the chat. So why is it uy instead of ux? And so it's uy because of the way that the stream function velocities are defined. So in order to get the x velocity from a stream function, you take the y derivative. And so basically, in order to get this, we integrated in y. Because we basically we need to get rid of that derivative there. So in order to cancel this derivative, we have to integrate dy, and when we integrate u dy, we get uy. Yeah. So that's a little bit of a a thing that's difficult to remember with the stream function. So that in order to get the x component velocity, you have to take the y derivative. So it's a little bit flipped. And so if you kind of remember that, then that kind of helps a lot. Yeah. Okay. And so sources and sinks, again, I combine them together because even though they're fundamentally different, their stream function patterns look the same. Okay? And so here's what a source looks like. So a source, you can kind of think of it as like, almost like a fountain that's kind of putting out fluid in all directions. Okay. And so there's going to be a point of origin. Okay. And so I'll give that denote by the dot. Okay. And then a source basically will have flow that's kind of all radiating out from it. All right. Okay. And a sink is kind of the opposite. So the sink, you can think of just like the sink in your faucet. Okay. Oh yeah, sure. Yep. Okay, so the sink you can kind of think of like the sink inside your faucet. So it's basically you're going to have flow that's going into the sink. Okay? So the flow is going down the drain. Okay? So even though these two are different things, you can see that their patterns look similar, where where we're basically going to have flow that's either going radially out from one point or all going in to one point. Okay? And kind of the term that we use to describe this is that our velocity vectors here are purely radial. Okay, and that means that they're radiating out like that. Okay. Okay. And so this the velocity vectors in this case, we're going to do it in cylindrical coordinates because it's a little bit easier that way. Okay. Right. And so we say that UR is going to be equal to minus M divided by 2 pi R. Okay. And this is going to be equal to 1 over R d psi d theta. Okay. And then U theta in this case is going to be 0. Okay. And this is minus d psi dr. Okay. Right. And so I'm giving the velocity here a little bit of a strange form, and the reason for that is because of how we define this m right here. So this m is a new variable. It's actually an old variable. It just kind of has a new name. And so this m right here, this is the flow rate. Okay. This is going to be the flow rate through our center. Okay. Right. And so because we have all the velocities either coming from or going into this this circle in the middle, we can kind of quantify in terms of how much fluid is actually going in there. So this m right here, this is the same as the q that we've been using before, but I'm going to change the symbol to m just because in potential flow they traditionally use this symbol m. So I don't want you guys to get confused if you're reading the book or you're reading other texts and they use M right there. So that's the kind of reason they did that. Okay? All right, and so if we integrate these guys basically same as before, we can get the following stream function. Okay? And so our stream function would be minus M over 2 pi times theta. Okay. And so this is the stream function for a sink. Okay. And you'll notice that for a sink that we have a negative sign out in front right here. Okay. And so in order to get the source, we basically just make this a positive number. Okay. And so for a source, we just make this negative into a positive. Okay. Okay. Any questions on this?
Yeah, Professor, does this follow something similar to like inflow outflow, kind of positive and negative factors?
You can kind of think of it in the same way, in that if you have a source which is kind of like outflow, you can kind of think of that as positive, and the sink is kind of like like an inflow because the flow is going into the dot. You can kind of think of it as the same way. Yeah.
All right.
Mm-hmm. All right. So the question is, are those two formulas U r and U theta? That's correct. Yeah. So these are the velocities in cylindrical coordinates. So because, or you can, I guess it's polar coordinates in this case. Yeah. And so we define the velocities in terms of that instead of x and y. Mm-hmm. Okay. And so before we move on to the next flow, which is a vortex, I do want to draw your attention to one thing, okay? And that's the fact that we have a 1 over r right here, okay? And so the way the velocity is defined is it's defined as 1 over r. So there's a few consequences to this. And so the first consequence is that as you get farther away from the origin or from the center, the velocity is going to decrease, right? So as r increases, our velocity will go down, okay? And that makes sense because if you think of it from a control volume point of view, as the flow kind of goes out, in order to maintain basic conservation of mass, the flow has to slow down as it goes across kind of a wider area, right? Because if you draw kind of a control volume that's like kind of like this, okay? So one thing that's close to the origin, then you would have a certain velocity coming out. But then if you draw another control volume out here, okay? So this control volume has a wider area. So in order to basically maintain conservation of mass, the velocity has to slow down as it gets farther away from the origin. Okay, so that's one consequence. And so the other consequence is what happens when r equals 0. Okay? And so when r is equal to 0, that's basically right when we're on top of our origin right here, right? And so when r is equal to 0, we have 1 over 0, which is infinity, right? And so what this formula is basically telling us is that we have infinity velocity at our origin, which obviously can't happen. Okay. And so when you have something like this, and this is not the only time we'll see this in potential flow. When you have a certain location where it kind of breaks all the rules of physics, then we call these locations singularities. Okay. Actually, let me write that on the next page just so it's a bit more clear. And so singularity is a very broad term, and I think it's overused in a bunch of sci-fi stuff. But in our context, a singularity will basically be used to describe a location where we get impossible flow. Okay. And so the example of a singularity that we just saw was, you know, an infinite velocity. Okay. And so obviously an infinite velocity can't happen because even light doesn't travel at infinite speeds, right? But the nice thing about singularities is that it's only at one location where we kind of break all the laws of physics. Okay? And so, you know, what we can say is that we can say that yes, you know, at this one location we break all the laws of physics, and you know, Isaac Newton and Navier and Stokes, they're turning over their graves. But you know, at every other location in our flow, you know, we actually get a very valid, you know, physics following flow. And so, you know, when we use potential flow, it's really important that we're aware of where all our singularities are, and that you know, just so that we can just avoid going there. Okay. Okay. So it's perfectly fine to perform analysis everywhere else on the flow, but for at the singularities, we're just going to ignore that point and just kind of assume it doesn't exist. Okay. And so that's a source and sink. So source and sink, you know, it's just kind of usually you just kind of follow the name. So it's just basically flow that's either going radially out or radially in, and then there's a singularity at the center where we just kind of avoid doing that. Okay. Okay. And so the next potential flow, so this is number 3, or I guess number 4 if you count source and sink as separate, but I count them as the same, is a vortex. Okay? And so a vortex, you can kind of think of it as kind of almost the opposite of a source and sink. Okay? And so, you know, the source and the sink, we had purely radial flow, and we had no rotational flow. And so the vortex is the opposite. So the vortex, we're only going to have just pure rotational flow. Okay? Okay? So in other words, you know, we're going to use polar coordinates again, but instead of UR, we're going to have only U theta. Okay. And so schematically, it kind of looks like just like a whirlpool. Okay. So we have our center. Okay. And then the streamlines are going to go kind of around in a circle like this. Okay. And so you can see here, you know, our flow is just basically just rotating about our center, which is right here. Okay? And so that's what defines a vortex. So a vortex where, you know, remember a source and the sink is purely radial flow, and a vortex is just purely rotational flow. Okay. All right. So on the next page, I'm going to give you the velocity, the velocity components, and also the stream function. Okay. Okay. Any questions on this? Okay. Okay, so the stream function for a vortex is given by the following. Okay, so we have psi is equal to minus, I think this is a gamma, okay? And we have the natural logarithm of r divided by 2 pi, okay? So this is the stream function for vortex. Okay. And so remember this, this also follows a sign convention. So this one's a little bit opposite because we have a negative that's naturally out in front, okay? But this, this parameter up here, this gamma, this is known as the circulation of the vortex. Okay? And so circulation basically defines how strong the vortex is. So, you know, the higher your circulation, the more strong the rotation is going to be. Okay? And then the sign convention for circulation is that if it's counterclockwise, circulation is going to be positive. But then if it's clockwise, then circulation is going to be negative. Okay. Okay. But then what you actually get for the stream function is opposite of that, because we have this extra negative that's out in front. Okay. Okay. And so that's the stream functions. And so let's solve for the velocity. And so we know in this case our velocity is just going to be in the r component, or in the theta component, sorry. Okay. And so our u theta, the way that we get that is we take the derivative of psi with respect to r, the minus sign. Okay. And so we get gamma over 2 pi r. Okay. Right. And then you can find ur as well, which is just, remember, d psi d theta 1 over r. Okay. And then what you get from this, since there's no theta here, you're just going to get 0. Okay. All right. Okay, so that's a vortex. But some of you might be saying, but wait, remember at the very beginning of our notes today, we said that we're going to assume that our flow is going to be irrotational. Okay. Right. And so irrotational means that you can't rotate, right? And so how can we have an irrotational flow but also have a vortex at the same time? This makes no sense. Okay. But in this case, we actually can have a vortex and be irrotational at the same time. So yeah, so the question of chat, does ur equal 0? So yeah, ur is equal to 0 because we just have purely just rotational flow. Mm-hmm. Right. And so notice on the previous slide, I call this an ideal vortex. So that's really key here. Okay. Okay. And so because this vortex is designed in a very specific way, actually, if you put an object in here, the object will kind of translate in a circle, but the object itself won't rotate. Okay. And I'll show you exactly what that means, but that sounds really paradoxical. Okay, and so here's kind of a picture, okay? And so let's say that, let's draw our ideal vortex again. Okay. Okay. And so say in this object, or in this vortex, we're gonna put a stick in there, okay? Oh, question. Go back a page, yes. Okay. Okay. And so in this flow, let's put a stick, okay? And so our stick has this rotation, or it has this orientation where it's horizontal, okay? And so as the stick kind of moves with the flow, the stick will move from here to another location, right? So it's going to move to this part of the flow. And so when I say that the flow is irrotational, what I mean is that the stick, it's going to be moving along with the flow, but it's actually not going to be changing its orientation. So the stick is still going to be kind of horizontal like this. Okay. And so, the stick is basically, you can kind of think of it as just going to move around in a circle around the flow just like this. So it's going to be translating, but it itself is not going to be rotating. It's not going to be changing orientation. Okay. And it's really trippy to see for the first time because it's the flow itself is going in a circle, and it looks like a whirlpool. But as you sit in the whirlpool, you're not going to actually change orientation. And so, you can kind of think of this like if you have like a whirlpool in the ocean too, right? You can sit in the whirlpool and you can not do anything, and you're just going to be rotating around just like this. So you're always going to be facing the same direction. It's just that your body is going to be, going around in a circle around the whirlpool, right? And eventually, you're going to get dragged into the whirlpool, and That's fine. Okay. Okay, so that's what defines an ideal vortex. So an ideal vortex will kind of translate objects in a circle, but it won't actually rotate them. Okay, and so the opposite of this would be kind of a non-ideal vortex. Okay, and so the opposite of this would be like a forced vortex. And I wish we had more time in this class because we're not going to get into anything. We're not going to get much more into vorticities, but spinning flow and vortices are actually really, really interesting. Okay. And so for a forced vortex, we have the spinning flow just like before. Okay. But instead of the velocity, you can see the velocity here also has this 1 over r. Okay. And so what that tells us is that for the ideal vortex, velocity goes down as it gets farther away. Okay. Okay. And so this is for a free vortex, or this is for an ideal vortex. Okay. So an ideal vortex, we have a maximum velocity near the center. Actually, we have a singularity again. And then the velocities then keep going down as you go farther away. And so a forced vortex is the opposite. So a forced vortex, our velocity is actually going to go up as we go farther away. Okay? And so a forced vortex actually looks basically the same as if you're spinning a solid object. Okay? And so another name for a forced vortex is rigid body rotation. Okay? And so in a forced vortex, you might have your stick right here, but as the flow goes, the stick is going to start to rotate. Okay, so you can see our stick here is kind of changing orientation as the flow goes, and that's for a forced vortex. Okay. Any questions on ideal vortices and forced vortices?
So you said it's the opposite. The velocity is going to go up the further you get away from the center.
Right.
For force.
Right. Yeah. So think of like a spinning record, right, or any kind of solid object that spins. And so you can define the angular velocity of that spinning, kind of just by that. And then in order to get the linear velocity from the angular velocity, you take r times the angular velocity. So as r increases, then your speed is also going to increase as well. So that's why forced vortices are kind of the opposite. The reason it's called a forced vortex is because you can kind of force it to happen by spinning. So if you imagine, you have your coffee and you take your stir and you spin it for a while, then the flow field that actually generates from that is actually that of a forced vortex, because you're kind of forcing it to spin with the stir. Okay. Okay. And so, again, with the forced vortex or with the free vortex, ideal vortex, we have a singularity at the center. And so we want to avoid doing any analysis there. Okay? And so finally, we come to the last ideal flow or potential flow, and that's a doublet. Okay? And so a doublet is kind of weird because it's it's not really, you can read the doublet, but it doesn't really tell you exactly what it is. Okay? And it's actually, a very special combination of a source and a sink. Okay. And so the way that a doublet is usually described in the textbook is that, say that you have, a source right here and a sink right there. And so our source, remember, we have flow that's coming, radially outwards. Okay? Okay. And our sink, we have flow that's coming radially inwards. Okay. And what the doublet says is that, we're going to take these two flows and then bring them closer together, okay? Okay. And so kind of the intuitive thing to think is that, these guys might just cancel out. Okay? Oh, so a question in the chat is a whirlpool the same as a vortex? So yeah, a whirlpool is definitely a good real life example of a vortex. Yeah. Mm-hmm. Or like a tornado is like another good example. Okay. So the intuitive thing to think is that if you bring a source and a sink close together, they're just going to cancel each other out. But actually, when you bring them, really close together and you put them on top, you actually get some really interesting flow patterns. Okay. And the way that you can motivate this is that let's draw the flow patterns that actually result from this image right here on the top. Okay. And so intuitively, what you would think is that the flow is going to go from the source and then go to the sink, right? And so we're going to have flow patterns that look like this. Okay. And so you're going to have flow, that's going to emanate from the source, and then it's going to end up in the sink. Okay. And so when you bring these close together, you can see that we have some curvature here in our streamlines. Okay. Once you bring them close together, then those streamlines basically just become like a circle. Okay. And so you bring them together, and you actually get a doublet flow, which looks like this. And obviously, I'm not doing a great job of drawing this, but this is basically what it looks like. And so you can kind of see why it gets the name doublet, because we kind of have these two kind of circular patterns, ones that forms on top of the doublet and one that forms below, right? And so the doublet, comes from the fact that we have like an 8 here. Right? And so we have, two circles that are on top of each other that kind of form a number 8. And the doublet refers to, we have two double circles that look like that. Okay. Okay. And so the stream function for the doublet kind of has a very special form. So it's not just, you add a source and a sink, because if you actually do just add those stream functions, you get 0. And so the stream function for a doublet has kind of a more special form. Okay. All right, so any questions on this before I get to the stream function?
So the doublet has opposite flow, or mirrored flow, I should say?
Yeah, you can kind of think of it as like mirrored flow. So you have kind of a circular, not really a vortex because it doesn't have the same origin, because you're basically going to have increasing circles like this, but they all kind of intersect at a point on the bottom. So it's not quite a vortex, because a vortex everything has the same center, but you have kind of this mirrored kind of circular flow kind of on top and on the bottom, and that's what forms the vortex, or the doublet. Sorry. Okay, so the stream function for the doublet is given by the following. Okay. So we have psi is equal to minus k sine theta all over r. Okay. Right? And so this k parameter here, this is known as the strength of the doublet. Okay. And so you can see, we again have 1 over r, and so we again have a singularity at the origin that we have to avoid. Okay. Okay. And so I don't want to say too much more on the doublet, because it's kind of its own weird thing. And a doublet, just by itself doesn't have that many physical significance. But once you combine doublets with some of the other flows, then that's when things, some magical stuff happens. Okay. And so those are our 4 kind of basic building blocks for potential flow. So before we go forward, I do want to kind of summarize. Okay. All right, so the first one we went over today was uniform flow. And so the most general form for uniform flow was given by the following. Okay. And so for uniform flow, we had psi is equal to uy cosine alpha and ux, or uy cosine alpha and ux sine alpha. Okay. Okay. The next one we went over was a source and a sink. And the psi for this was equal to plus or minus m2 pi theta. Okay. Just remember the sign that you choose for this is going to depend on if it's going to define whether it's a source or a sink. Okay. Next we have our ideal vortex. Okay. Again, this is going to be plus or minus plus or minus gamma over 2 pi ln of r. Okay. And then finally we have our doublet, where the stream function for this is going to be minus k sine theta over r. Okay. And so these are our 4 building blocks. Okay. Okay. And so before we move on, I do want to kind of highlight something, a feature for each of these different, stream functions. Okay. Okay. And that each of these stream functions have a variable that's circled in purple. Okay. And what those purple parameters, what they represent is the strength of the stream function. Okay. And so every stream function, they all represent kind of fundamentally different flows. But we can kind of increase the power or decrease the power of these stream functions and the flows by increasing or decreasing these parameters. Okay. And so, for example, let's look at uniform flow, right? And so for uniform flow, our strength parameter there is big U, which is just simply just the velocity of our uniform. Okay? If we increase big U, then the strength of our uniform flow is going to increase because the amount of velocity that's going in there is going to increase. Okay? And if we decrease U, then our flow is going to slow down. It's going to become less strong. Okay? And again, for the vortex. So the vortex, our strength parameter is gamma, and that defines, the circulation or, how strong or how much our vortex is spinning. Okay. And so these are important because these are the way that we can kind of basically modify our stream functions to make to have them give us the flow that we ultimately want. Okay. All right. Any questions on this? Okay. All right. So one other thing that I'll note is that I don't remember if I said this explicitly, but for all of these potential flows and just for potential flow as a a field in general, we assume that there's no viscosity. Okay. And so there's no viscous stuff going on in potential flow. Okay. Which might seem like a pretty big assumption because viscosity is a pretty big thing. We haven't really talked about it all too much in this class, but with Navier-Stokes we'll start to talk about it quite a bit. Okay. But the kind of the big upshot for having no viscosity, or the big consequence for in potential flow, is that if we have a solid surface in our potential flow, then there's no way for the velocity to stick to that surface. Okay. Or in other words, we can say that our flow is going to slip at solid surfaces. And so normally if you have a fluid that's flowing past a solid object, the fluid is actually going to stick to that solid object. So so the fluid is going to adhere to that solid. Okay. But the only way that fluid can actually adhere to a surface is through viscosities. And so if we kind of remove viscosity from the equation, then we don't actually have, there's no way for the fluid to stick. Okay. So this might seem like a really big assumption because viscosity, is something that's really important for flows. But for a lot of the applications where we use potential flow, where a lot of it is in like aerospace applications, mostly like in airplane design. Okay? In airplane design, basically, if you can kind of think of an airplane flying through the air, we have an airplane, which to us is a big object, but to the bigger environment and the world, it's a very small object. So you have a very small object in a very large flow field. Okay. And in those situations, because our solid surface is relatively small compared to the big flow, then we can assume no viscosity, and we don't really lose anything from it. So the question is another term for an ideal vortex a free vortex? So yeah, another term. So you can call it an ideal vortex a free vortex as well. Yeah. So those terms are interchangeable. And it gets the name free vortex because it's a vortex that's not forced. So you're not kind of forcing it to spin with like a stir or something. And so kind of the best place to view an ideal vortex or a free vortex is to fill your bathtub up with water and then just pull the, and then just, release the drain. And then what you should see in that case is that the flow starts to rotate as it goes down the drain. Okay? And so that's an example of a free vortex. It's actually a sink and a free vortex at the same time. But the fact that the flow is spinning without you having to actually actively do anything to it, that's a free vortex. Yeah. Mm-hmm. Yeah. Tornadoes, tend to be free vortices as well, just because it's a vortex, but the environment isn't actively causing it to spin. It's just kind of forming naturally just from the pressure differences that occur in the environment.
Yeah. So anything that's ideal or free would be considered like something that can essentially happen on its own without us stirring the coffee or inducing a flow.
Exactly, right. Yeah. Mm-hmm. All right, any questions on this before? So the next thing is we're going to start to combine some of these potential flows, and this is when things get exciting. Okay.
Actually, you had mentioned aerospace and how airplanes move through the air and sometimes create vortices on like their wingtips or behind the stuff or whatever. Did you say that was a naturally occurring like ideal vortex, or would that be it's not a forced vortex?
Yeah, so that would actually be a free vortex as well, because so what Steven's referring to is that if you have an airplane flying through the air, or anything flying through the air, you can look at a bird too. Kind of off the ends of the tails, you have these things called trailing vortices. So you have these vortexes that form because you kind of have a solid object that's kind of slicing through the air, so it's kind of causes these vortices. And so for the brief instant, or for the time that the vortex is attached to the wing, that's actually a forced vortex because you're kind of forcing it with the solid object. But as soon as that vortex kind of peels off the wing and it kind of falls off, it's still going to continue to rotate. But we're not actually forcing it with any kind of solid object. So that'll be kind of a free vortex. And so eventually those vortices kind of die down because of a lot of factors in the air. But for the time that those vortices peel off of a wing, and come off, those are going to be free vortices because we're not forcing it after it peels off. Yeah. So the question is, does it naturally flow in one direction? So yeah. So free vortices, they'll naturally flow in one direction, and it's getting into that direction is a little bit complicated because it kind of depends on the situation. But if you're talking about like a bathtub and like a tornado, those kind of form due to kind of pressure differences in between the outside the tornado and the inside, and that kind of naturally pushes flow in one direction. So that's the best kind of like 10-second explanation I can give without getting too much. But if we get more into it kind of later on, then I think we'll get into it back then. But I think for now, I just want to focus on potential flow. Yeah. Mm-hmm. Yeah. So for tornadoes and specifically, I think the rotation of the Earth and whether you're in northern hemisphere, southern hemisphere, they all have an impact on it too. Yeah. Mm-hmm. Okay. Okay, so that's you know, that's all our potential flow building blocks. So now let's actually start to combine them together. Okay. So here's where things get really interesting, because you know, up to this point, you know, all the potential flows that we've covered, you know, you can just define those in terms of the velocities, and that's, you know, that's actually more convenient than a stream function. But you can't just take, you know, the velocities for these different things and add them together. So the way that you actually combine flows together is to actually add up their stream function. And so another term you'll see for this, which you might recognize from your math classes, is superposition. Right, so we're going to superimpose or superpose these stream functions together. Okay. And so, you know, before we start, I do want to make kind of one note, in that, you know, I've been drawing lots of you know, pictures of streamlines, right? So let's look at our uniform flow again. Okay. And so these arrows represent the streamlines for the flow, because they kind of act because they kind of tell you which direction the flow is. Okay. And so another way I want you to interpret these streamlines is that you can kind of almost think of them as solid boundaries as well. Okay. Which is a really weird thing to think, because, you know, we have flow that's going this way. How can you just pretend that a part of the flow is a solid boundary? Right? And so, you know, the reason I want you to think of that is because, you know, if we have our flow arrows going like this, then there's actually no way for a flow or for fluid to actually go across the streamline. Right? And so this is impossible right here, because the flow is going all in one direction. You know, we have no flow that's actually going perpendicular or across these streamlines. Okay? And so what we can basically do is that if we know all our flow is going in this direction, we can say that, you know, we actually have a solid object like this. Okay? Right? And this is basically the same thing, because, you know, the flow above here is not aware of the fact that there's a solid object there, because, you know, that's where the streamline is just going. Okay, so we have no streamline that's actually going into the solid object. And so basically, wherever I draw my arrows, you know, that line will basically kind of act the same as a solid surface. And since we have no viscosity here, you know, we have no sticking to that solid surface. Okay. And so when we combine these potential flows together, you know, we'll start to see that they kind of form some interesting shapes and some interesting solid objects. Okay, so let's do kind of the first example here. And so our first example will be what's called the half body. Okay. Okay. And so what a half body is basically a combination of a source and a uniform flow. Okay. All right. And so, you know, in order to get the stream functions, we're just going to simply add them together. And so our total stream function is going to be sum of the stream function for a source and the stream function for a uniform flow. Okay. And if we plug in their formulas for this, we get u times y plus m over 2 pi times theta. Okay. But here we have kind of a weird combination of Cartesian coordinates and polar coordinates. So let's put them all in polar coordinates. Okay. And so what I'm going to do is I'm going to substitute in for y. And so in polar coordinates, y is equal to r sine theta. Okay. And so we have u r sine theta, okay, plus m over 2 pi times theta. And that's our streamline for our half body. Okay. And so on the next page, I'll draw the picture for you just to kind of show you what it looks like. Okay. But are there any questions on this before I do that? Okay. Okay, so the half body looks like this. So we have basically, I'm gonna draw our Cartesian axis here. Okay. And so our first part of the of our half body is our uniform flow. And so we have uniform flow that's coming in just like this. Okay. Okay. And then our other part of the half body will be our source. Okay. And so our source, remember, we have just a center at our origin. Okay. And it's going to be radiating flow outwards like that. Okay. And so when these flows interact, they create a body that looks like this. Okay. And so there's going to be a certain point on the x-axis where the two velocities basically cancel out. And so this point right here will be a stagnation point. Okay. And so remember what a stagnation point means. So a stagnation point basically just means that the flow is going to be zero there. And then from here, the flow is going to basically go like this. Okay. And so you can see why it gets the name half body, because we have a, we can see that we have this body right here. Okay. And it's only clearly defined on half of its length, because on the other half it kind of extends towards infinity. Okay. Okay. And so the width of this half body will be defined as 2 pi b, and I'm going to define b in a second right here. Okay. Okay. And so that's what the half body looks like. So it's intuitively, you can kind of almost think of it as you have kind of a stream of water, like, you have water in a river or something, and you stick a boulder in there or something. So if you stick a boulder, the flow is going to go around the boulder, and it's going to kind of keep kind of going, splitting off like that. So that's intuitively what I like to think of it. Okay. Okay. All right. So let's start quantifying these. Okay. And so, I said I'm going to define this location B right here. And so this location B is actually this length in between the source and the stagnation point, okay? And so what we can say at location B, the velocities from the uniform flow and the source perfectly cancel out. Okay. And so we can basically solve for B by taking the velocities from the uniform flow and the source and setting them equal to each other. Okay? And so we can say that the source velocity is going to be equal to m over 2 pi b. Okay. So normally there's an r right there, right, for the source, and this is equal to big U. Okay. And we solve for b. This tells us that little b is equal to m divided by 2 pi u. Okay. And so this b basically depends on the ratio of the strengths, right? So remember, we define the strengths of our potential flow to be like this, right? So this m right here is the strength of the source. Okay. And so you can see if our source is stronger and we increase m, then the b is going to get farther out. Okay. And then meanwhile, this u right here, this is the strength of uniform flow. Okay. And so if we increase the strength of the uniform flow, then the stagnation point moves closer to the origin. Okay. Okay. And so another important formula that we have is going to be the formula for the body. Okay. Okay. And so that's going to be given by y is equal to b pi minus theta, okay? And so that's basically going to be the function that defines our solid body like this, okay? And so if we were basically to plot that curve, that's what it would look like, okay? But if we want to put this totally in radial coordinates, where we substitute y is equal to r sine theta, we get the form that's a little bit more useful, okay? And so the formula for the body will be like r is equal to b pi minus theta all over sine theta. Right? And so for this half body, you know, the formula for the surface is going to be something that's really important, because that's we're going to use that for our calculations. Okay. Okay. Any questions on the half body so far? So the question is capital U only used for uniform flow and not to be mistaken with lowercase u? So that's correct. So I'm going to use capital U here to define, basically, you can almost think of it as like the speed of the uniform flow. And so in this case, you know, big U and little u are the same, because, you know, the flow is going in the x direction. But big U, you can kind of think of it as how fast the uniform flow is going. And little u is just the component, the x component of the uniform flow in the x direction. Yep. Okay. So that's, you know, that's the geometry of the half body. Okay. And so let's talk about a little bit more. Okay. And so let's talk about the width. Okay. So I've already kind of defined this in the figure, but the width of the half body is just going to be 2 pi times b. Okay. And so, you know, when I say width, what I mean is like width kind of far away from the origin, because, you know, eventually, you know, the half body is going to continue to grow, but up to a certain point, you know, it's going to stop growing. It's just going to, you know, kind of reach this kind of asymptotic flow like this. And so the width of that region is going to be 2 pi times b. Okay. We can also compute the velocities. Okay. And so remember, the velocities we can compute by taking the derivatives of the of our stream function. Okay. And so UR, so we're going to be in polar coordinates, is going to be 1 over r partial psi partial theta. Okay. And so this is going to be big U cosine theta plus m over 2 pi r. Okay. And so that's the radial velocity. And so the rotational velocity, u theta, is given by minus d psi, or partial psi, partial r. Okay. And this is going to be minus u sine theta. Okay. Okay. And so those are the velocity components, but oftentimes it's useful to take the magnitude of these components. Okay. Another name for the magnitude of the velocities is going to be speed. Okay. Okay. And so the way we do that is I'm going to give that the symbol u surrounded by walls squared. Okay. It's simply going to be ur squared plus u theta squared. Okay. And so, you know, this is going to involve some foiling, because we got to foil this guy, and then we got to square this guy. Okay. And so if we work out the math, it's going to be u squared plus cosine theta divided by pi r plus m over 2 pi r squared. Okay. And so, you know, I'm kind of skipping the steps in order to define this, but you know, one important thing that's useful for this is to remember your trig identities. Okay. So remember, sine squared plus cosine squared is equal to 1. Okay. So that's going to be really useful, especially as we start doing problems. Okay. All right. And so another way to express the speed, and so this form is perfectly fine right here. Okay. But it puts everything in terms of u and m, which are kind of, you know, fluid mechanically fluid mechanic-y kind of parameters. Okay. What could be more useful sometimes is actually to express the speed in terms of b, right? Because b right here, that's a geometrical quantity, and so that's kind of the, you can almost think of it as a parameter of the width of the streamline. Okay. And so if we express the speed in terms of b, what we get is the following. Okay. Okay. And so we get u squared times 1 plus 2b over r cosine theta plus b squared over r squared. And so this form is nice because it puts everything in terms of just the geometrical quantity. So we don't have any m's or big U's kind of floating around. Okay. All right, any questions on this? Okay. All right. And so why did we bother looking for the speed? And so, you know, the reason we looked for speed was that we can actually take this and apply it to another old friend, which is Bernoulli. Okay. Because if you think about it, we're actually in the perfect situation for Bernoulli, right? Because if you remember, for Bernoulli, we had to satisfy our 4 assumptions, right? So our 4 assumptions for Bernoulli was steady, it was incompressible, it was along a streamline, and we have to ignore viscosity, okay? And so for potential flow, we actually have all 4 of those guys satisfied. And so, you know, what we can do after we find speed is that we can use Bernoulli to solve for pressure, okay? Okay. And so basically what we can say is if we have some kind of reference point, okay? Remember, Bernoulli, we can only form comparisons in between 2 different points. And so at our reference point, let's say that we know the speed and the pressure at that point. Okay, so we'll call the speed U naught, and the pressure will be P naught. Okay. If we know the speed and the pressure at one point, we can actually find the speed and the pressure everywhere. Okay. So what we can say is that we can have P naught plus 1/2 rho U naught squared, okay, plus you know, the height differences, but I'll leave those out for now. Okay. This is going to be equal to P at plus 1/2 rho U squared. Okay. And so this is a speed U. Okay. So this here is the quantities at our reference point. Okay. And here is going to be the conditions at any other point. Okay. And so on the previous page, what we have is we have an expression for this. Okay. And so we know what U squared is anywhere just from the previous page just by taking the magnitude of the velocities. Okay. And so basically what we can do is we can solve this expression for P, which is going to be the pressure anywhere. Okay. All right. Any questions on this?
Yeah, you said that U in Bernoulli for this one is speed.
Yes. Yeah.
Kind of from what we did in the last equation.
Exactly. Yeah.
Sure.
And so the way that you know, the way that these potential flow problems typically progress is that the first thing you're going to do is you're going to form the stream function based on, you know, the geometry of the flow. Then from there, you're just going to take derivatives and get the velocities. And then if the question asks you for pressure, you're going to find speed, and then plug it into Bernoulli and then solve for the pressure distribution anywhere in the flow. Yeah. All right. Yeah, so those are absolute signs. Okay, so I'll stick around for questions for a bit longer, but that's all we got time for today. It's 9:45. So there's a new minute paper up on Canvas. So so if you want to fill that out, definitely feel free. But if not, have a great weekend, everyone. You can probably start working on the homework. So we haven't done an example with potential flow, but I've given you everything that you need to do in order to solve that potential flow problem. So you can give that a try. And of course, anytime you have any questions, you can always reach out. Thank you everybody for tuning in today. Have a great weekend, and I'll see you guys on Monday.
Thanks, Dr. Tran.
Thanks, Stephen.
Professor?
Yep.
Can you go back one page?
Sure.
Oh, can you go back to the half body page? Sorry.
Yep. This one, or the I guess this is the image, but then the other one.
This
okay.
one works. Yeah. Can you explain how you got the URB equation?
Yeah. So basically, we basically have a source and a uniform flow, right? And so our UR for the source is m divided by 2 pi r, right? And so all I did here was I evaluated this UR at r is equal to b. So I just took this formula for the source and I just plugged in r is equal to b right here. And that's how I got this guy.
Oh, okay.
Yeah. And so what I did was I set this equal to big U, which is the velocity of the uniform flow. And so what I said is that those two guys at the stagnation point have to be equal to each other because they got to cancel out.
Thank you.